Welcome to CS 320, Chapter 9. And this chapter is called Regular Languages. So what is a regular language? Any language that can be defined by a regular expression, finite automata, or a transition graph is a regular language. So if we can define a language using one of these three defining mechanisms, then that language is considered to be regular. Now we're just going to look at a few properties of regular languages for the rest of this chapter. Now one property defined in Theorem 10 says that L1 or regular languages are closed over the union, concatenation, and starring. So we already proved most of this using Kleene theorem in the previous, in chapter 7. So this is pretty obvious and easy that we can just union two languages together, or concatenate two languages together, or star a language. And when we do that, the resulting language is also regular. So when I say something is closed under these operations, that means if something is a regular language, and then we do, or two things in this case, and we do an operation, that produces a new language that is also regular. So if this is regular and this is regular, then this language is regular. If this language and this language are regular, then so is concatenating the two together. If language 1 is regular, then so is starring the language. Now, this proof is pretty easy because these are operations in regular expressions, and we also did it in Kleine's theorem, but you can look in the book for more details about that. Now let's talk about the complement of a language. The complement, usually denoted by an apostrophe, it means the opposite or not. And you might have seen this symbol in predicate logic or other areas of mathematics. Now, if we have the language, all words that have a double A in it, and we complement it, and that means take the opposite, then that's all words that do not have double A's in it. Now, the question is, if a regular language, if we complement it, if we're guaranteed to get a regular language as its complement. And according to Theorem 11, yes, that is true. So what Theorem 11 says, if L1 is a regular language, or is regular, then so is L1 complement, or the complement of it. And we'll go over the proof in a little bit, but just so you know what this means, L1 being regular means that it can be defined by a regular expression, a finite automata, and a transition graph. So if L1 is regular, then we can also define L1 complement with a regular expression, a finite automata, and a transition graph. So let's go ahead and do the proof of that, and I'll just do a little example to show this proof. We'll do all words, or just the language that has the word ABA and ABB in it. So let's go ahead and create a finite automata that accepts the language with just these two words in it. So this finite automata accepts the words ABA and ABB, but only those words. If we read another letter, we go to this state down here that rejects everything, and that does need a loop that just loops on A and B. And of course, if we don't get A at the beginning, or a B at the beginning and an A as the second letter, then we go to this state as well and reject it. Now, what if we want to take the complement of this language, or all words that are not ABA or ABB? So not this word or not this word. Well, we do the same thing with any finite automata. We erase the final state, and then we make all the states that were not a final state become a final state, including the start state. So basically, we just flip. If it wasn't a final state before, it is now, and if it was before, then it is not. And now we have a finite automata that accepts the complement. Now, Theorem 12 states that if L1 and L2 are regular, then so is their intersection. And there's a couple of ways to prove it. One way is using De Morgan's law. You probably studied about De Morgan's law when you studied predicate logic, but it also applies to sets. So if we complement both languages and union them together and then complement the result, then we're left with the intersection of two languages. And since these are all operations that guarantee a regular language as a result, there's no way that we can ever jump out of having a regular language. So just so we can see this happen visually, if we take language L1 and complement it, I'm going to highlight everything that is not in language L1. So that's everything that's outside of the L1 circle, including the stuff that might be in L2. Now, if you notice, what I did not highlight is all of this, including what's called the intersection between these two sets. Let's go ahead and do the same thing with L2. So I'm going to cross out everything in L2, or that is not in L2. So that's L2 complement. Okay. And if you notice, I didn't cross out anything inside of here, which also includes the intersection. So all the words in L1 complement and L2 complement are everything except this intersection between the two of them. So that's this part right here. We complemented both languages, combine them together, and we get everything except that intersection. Well, one more complement, and now we're left with the intersection, which is this symbol right here. So that's one proof of Theorem 12. Now, another proof of Theorem 12 can be, going back to Kleene theorem, when we intersect or when we union two languages together, like this, remember how we combined two finite automatas together? And in the end, we made a final state. So we had two finite automatas, one finite automata for this language and one finite automata for that language. And we took their final states and we said, oh, if it's a final state from this finite automata or this finite automata, then make it a final state. Well, in the new rule, to get the intersection, we make sure that it's a final state for the first one and the second one. So only states that contain the final state for both of these will become the new final state, and that'll create a finite automata that just accepts the intersection. So there's an example of that in your book, and you're free to read it. It starts on page 175, and you can see how they create a new finite automata that only accepts the intersection out of two other ones.